Good morning, everybody. In this particular session, we will learn the basic theory which everybody needs to know and is very simple in a layman's term. We will try to understand what exactly is this remote sensing. This theoretical base will help you all throughout, no matter what kind of project you are taking up and how further you want to build on this. So let's talk about remote sensing. What you see on this in this picture are different types of remotes, isn't it? These are the ones that we use to operate our TVs or maybe a fan these days, an AC or any electric appliances. The remotes basically help us without getting up from our place. We can hold this remote and remotely control the appliance that we intend to work with or that we intend to use. Right? So that is called a remote, right? Now, the other word that this particular process has is sensing. Humans have five different senses. We can taste, we can smell, skin that helps us to realize that somebody is touching us or something is touching us. We can see, so sight, and also we can hear, right? So these are the five senses that humans have. Now, these humans try to devise a sensor or a device that that human tries to bring as close as possible to his own senses. That is an appliance or a sensor that can collect information using these five senses. But as we know, it is pretty difficult to achieve all the five senses because humans are just perfect, isn't it? What these five senses do for us? They collect data. They collect information from our surrounding. We can see, we can taste, we can hear, we can sense if somebody is touching us, so the touch feeling, and also that we can smell. But these sensors that are used in remote sensing, they may not be able to do all these five different functions or collect information using all these five senses. Sorry. Coming to a satellite. What is a satellite? A satellite is basically a vehicle that carries these sensors to the space or to maybe um, to the space. However, if it is a drone, then it might be taking it into the air high up above the surface, not really into the outside atmosphere or not really into the space, right? So a satellite is like a vehicle that carries different sensors which are manufactured by humans. And what these sensors do, they look at the planet from very far up above such that they can collect largest piece of information from the planet, if not the all. So it keeps collecting information in parts and parcels. So the process of remote sensing is basically collecting information with the help of sensors mounted either on a satellite or a drone or a plane without coming in direct contact with the object or the planetary feature. Which are these planetary feature? Built up area, buildings might be there, rural areas, paved roads, bare soil, grass, or maybe agricultural land, water bodies, forests. These are the different planetary features. Now, to be able to see these different features on the planet, the satellite has to have, or the sensors have to come into illumination. There has to be some light. Often this light is received from the sun. So from sun, the solar energy is incident upon the planet and then it is reflected back because of which the sensor collects information. Now, There are two types of sensors or two types of remote sensing process. One is when solar radiation is used by the sensors or by the satellite to collect information, then it is called a passive sensor. Okay, it is passive. That means what? At night when sunlight is not there, it will not work. It won't be active. But on the other hand, we have active remote sensing or active sensors. They have their own source of illumination using which light is or energy rather is sent towards the planet, and then as it bounces back it brings information from the planet's surface or the different features that are making up the planet's surface. Coming to this passive sensor, because uh, whatever we understand about the kind of energy that we receive from sun will also become applicable to active sensors wherein there is its own source of illumination. But this electromagnetic radiation is what we receive from the sun. It has varying frequency and it has varying wavelength, right? So lower frequency, sorry, higher frequency, smaller wavelength, and as the wavelength increases, frequency reduces. This electromagnetic radiation has essentially two components, both of them vibrating at perpendicular to the direction of propagation of the light. These are electric field and magnetic field, both of them are orthogonal to one another. Coming to electromagnetic spectrum. So we have understood what is electromagnetic radiation. Electromagnetic radiation has two components, one magnetic and one electric, both of them orthogonal or perpendicular to each other as well as to the direction in which this light is propagating. Coming to electromagnetic spectrum, as we said that frequency mm, varies along the electromagnetic spectrum as well as the wavelength uh, differs. Higher frequency, lower wavelength, and as the wavelength increases, the frequency keeps reducing. Our solar radiation is an electromagnetic spectrum. That means it consists of different types of radiations that are sent towards the planet, which consists of gamma rays, X-rays, ultraviolet rays, and then we have a small slit, which is visible light with pure colors that we see. Humans don't see these colors, humans don't see these as well. So visible light and then infrared and then radio waves, okay, and it goes on and on and on. Now, this remote sensing is a process wherein you will find humans involved, the satellite sensors are involved, energy sources involved. There is a target, a feature that is lying on the planet that is also involved. There has to be a processing station where the data will be collected from the sensor or will be downloaded, and then it will be pre-processed or used by humans. And then ultimately that data will be applied to solve some real life problems. This electromagnetic spectrum that we saw, as we know, it is made up of different types of radiations. Gamma rays, X-rays, ultraviolet rays, they usually don't reach the surface of the planet. Essentially because they are either absorbed or reflected back into the space by the atmosphere. Ultraviolet rays, as we know, they are absorbed by the ozone layer. Visible light is something that penetrates to the surface of the planet, and infrared also, radio waves also, microwaves also. But the problem is humans see only this visible light. They don't see infrared or radio waves. They are there, they do interact with the features that are lying on the planet, but then we don't really see them. That is the reason why um, uh, that is the reason why we are showing that we are calling this visible light that is pure. It is many colors. Now there are different features that are present on the planet. We have cloud, we have water body, we have dry grass, we have vegetation, we have snow cover. Right? These are the different features that we are taking for now. This you see that the wavelength increases and the um, frequency reduces along this. Okay, somewhere here that is zero point 0.4 to 0.7 we have visible spectrum. Okay, until here we have visible spectrum and then we have infrared and then we have radar waves, microwaves and all. Okay. So now here let's look at vegetation. You see here, this is with your no, violet, indigo, blue, green. So the moment we come over green, you will see slight uh, peak in reflectance. This is the wavelength on the x-axis, on the y-axis we have surface reflectance. So you will see that violet, indigo, blue, and on this side red, orange, yellow. These are the colors which are absorbed or have lower surface reflectance for vegetation. But this is the portion of green. This is where you will see green is reflected and is not absorbed by this vegetation. And that is the reason why we perceive vegetation as green. So if any of your friend is wearing yellow color, that means what? All the other colors are absorbed and only yellow is reflected back. And because it is reflected back, your eyes perceive yellow color and the friend's t-shirt appear yellow. Okay. But if humans were to see near infrared radiation, then vegetation would have not appeared green to us. It would have appeared near infrared in color. But because we don't know what kind of color exactly lies in near infrared, how that particular color would look, we don't really know. And what we see is that vegetations appear green to us because that is the color that we see. But compare the reflectance of green color with that of near infrared. You will see that near infrared has a higher surface reflectance for vegetation. That means if we were to have two sensors, one operating at green color, that means it can see only green color, and another near infrared, then this green sensor will be less efficient in identifying vegetation as compared to that of near infrared. A near infrared sensor, a sensor that can sense near infrared surface reflectance, will be able to distinguish vegetation very clearly from any other. So you see that sharp rise in reflectance, surface reflectance after red color, that is in infrared region. Okay. So this near infrared is basically warmth giving radiation. So if you go out in sun, then you will see that you will feel warm, isn't it? It is not because of the visible spectrum. It is rather because of this infrared, thermal infrared or infrared radiation that brings warmth to us. Now let's go to water. Okay, let's go to water. So what you see, water reflects very high in blue, indigo, that region, and then slowly its surface reflectance reduces towards red. And as it reaches near infrared, it becomes almost negligible, which means what? Almost all of the near infrared radiation is absorbed by the water bodies. Because it is warm, no? The moment you bring some warmth to water, what it will do? It will readily and quickly absorb it. Now, when we will expect near infrared to reflect from the water body? Only when these water bodies reach boiling temperature. Only when these water bodies reach boiling temperature, they will stop absorbing any further energy, and only then what will happen is that some near infrared radiation will be reflected back. As we know that water cannot reach 101 degrees centigrade. It will reach 101 degrees centigrade only when all the water from this water body is evaporated, and then there is absolutely nothing to show you that 101 degrees centigrade. Correct, no? In a very ideal case scenario I'm talking about. Similarly, look at the dry grass. Dry grass also shows similar trend. That is, It reflects very low. It's a negative trend when we compare it to water body. It shows higher absorption or lower surface reflectance in violet indigo color, whereas as we reach red, the wavelength increases and the frequency reduces. What happens? It starts absorbing, sorry, reflecting. And as it reflects again in near infrared, you will see that this dry vegetation as well will stand out very distinct. Same is the case with our green vegetation as well. Coming to snow, you will see that fresh snow, very fresh snow, no? Uh, it reflects very nicely within the visible spectrum. It keeps reflecting the visible spectrum very nicely. That is why it appears white. No? Similarly, clouds you will see appears white. That is why they are reflecting away almost all or up to 90% of whatever visible range radiations that falls on it with your color. But as the wavelength increases and frequency reduces, what is going to happen to the surface reflectance? It will be reduced. That means this radiation will be absorbed. Okay. Now, that is why you will see that some microwave sensors like that of Ka-band or Ku-band, they do not interact with the snow surface or the clouds. They penetrate through the clouds, and that is why we use synthetic aperture radar waves to sense the topography of the surface, or also to measure the depth to bedrock through the glacier and things like that to measure the volume of the glacier. There are four types of resolution when it comes to satellite data. We have to be very careful about these four types of resolution. Which are these four types of resolution? One is spatial resolution. This spatial resolution talks about the size of the pixel or the clarity of the scene. The smaller the size of the pixel, better or complex information will be captured by the sensor. But if the spatial resolution is low, that means the pixels are huge. That means it has a lower clarity and less of information is picked. So within this one pixel, what has happened? A lot of region has been meaned out. Its surface reflectance has been averaged out, and that particular value you get, which means lower information, less of information. The complexity is sabotaged. Then comes temporal resolution. While selecting satellite data, you have to also be bothered about temporal resolution because the satellite keeps revolving around our planet, and on its way through these orbits, what it does, it keeps collecting pictures. So that means what? After every certain period of time, it appears back over the same space. Maybe after 1 month, maybe after 2 months, maybe after 7 days, maybe after 5 days, maybe after 16 days, it comes back over the same space over the planet and captures another picture. Because of which, if at all there were any changes between this period, we get to understand how the changes are occurring. That is temporal resolution. Okay, so temporal resolution or repetitivity also we have to be bothered. Next is radiometric resolution. Now, the sensors that we have mounted onto the satellite, they are sensitive to a range or a bandwidth of that spectrum, which means what? This range can be very narrow. That means energy coming at a very narrow range of frequency and wavelength can be sensed, or it can be slightly wide. That means a larger range can be sensed of frequency and wavelength. Now, if we have a sensor that has a wide bandwidth, that means it is sensitive to a wider bandwidth of the spectrum, then it will collect uh, information which has a lesser clarity or lesser information will be captured. So all these areas you will see here, the shadow and the wall maybe of this particular building, both of them are seen same, right? It's not able to discriminate. Why? Because both these radiations that are coming, or the frequency and wavelength that is being received at the sensor is not able to discriminate between them. Everything is being shown as homogenized. So this radiometric resolution also we have to be bothered about. Whereas if the sensor is very sensitive to even the narrowest range, then what is happening? It is able to distinguish between the shadow and the um, wall, right? Coming to spectral resolution. Now these sensors at times are widely spaced. For example, this is Vibgyor color, right? So consider this to be Vibgyor range. Okay. So one sensor senses blue color, another senses green color, another senses red color, another senses deeper red, that is infrared region, right? But what if we mount multiple sensors within this range? So the conjugate bands, when sensors are multiple sensors are mounted such that they are very contestedly spaced, or in the sense that very closely spaced, then we get a higher spectral resolution, a lower spectral resolution, wherein these sensors are sensing uh, a given spectrum range at a wider distance. Closely spaced, then they have a higher spectral resolution. So spatial resolutions are of two types: high spatial resolution, low spatial resolution. You must have understood this. High spatial resolution means smaller pixel. Low spatial resolution means bigger pixels. High spatial resolution, smaller pixel means you get more information. Low spatial resolution means bigger pixels, you get lesser of information. Spectral resolution can be multispectral or hyperspectral. When multiple sensors are collecting information um, within a given spectrum range, then we will call it multispectral. But if these sensors are very closely spaced, the space between them is very less, so that they are sampling every bit or every other bit of this spectrum range, then we will call it hyperspectral. So here you can call this hyperspectral, and this is multispectral. Hyper means very closely spaced sensors which are able to sense almost a big portion of this electromagnetic spectrum range. Then temporal resolution, high temporal resolution, this will help you understand what are the growth stages of vegetation. Low temporal resolution, maybe land cover you can study, not seasonal change, but yeah, seasonal also you can study. High temporal resolution, maybe every day a particular sensor takes picture of the same part of the planet. Low temporal resolution means maybe after 15 days it takes, or 1 month it takes, like that. Okay. So this is relative sense. So if you have a sensor that is collecting imageries at every second month and another at every 2 weeks, then 2 week will be higher temporal resolution. Then comes the radiometric resolution. High radiometric resolution is a sensor with high radiometric resolution can detect subtle differences in radiation intensity, allowing for more detailed analysis of surface features. Whereas low radiometric resolution is wherein sensors with low radiometric resolution may not be able to distinguish subtle differences in radiation intensity or potentially obscure details in the data. For example, here, how you saw that the shadow of this building as well as the walls of this building is being shown at the same reflectance. So that is it for the day. We will stop here.